Hi, welcome to topic 10.4. This is the final video of this particular unit. This is called dielectrics. So there's going to be a little bit of overlap with the last video because capacitors are essentially like special dielectrics. So we talked about that dielectric material that goes between the plates. Well, that is just simply going to be air for a capacitor and something different here for dielectrics. And what you can see is off to the right there is a chart of dielectric constants for the materials. And we'll figure out how you can calculate those, and then how can you calculate another value called the material permittivity, okay, based on those numbers. All right, so let's dive into this. So a dielectric material, what happens is the electric charges aren't allowed to move as freely as if they were in a conductor. And what happens then is it polarizes, the material gets polarized because of the external field coming into it. So remember, the electric field is created by the difference between the plates, not necessarily the dielectric material. Okay, and so what happens is that material becomes polarized, thus creating, this change in the electric field inside. All right, so we talked about in capacitors, the dielectric constant for a capacitor is 1 because it's air, right? And technically, it's a vacuum. Because if you actually look, air has a slightly different value than the vacuum. But each material, each dielectric material has a constant value called the material electric permittivity. On the AP test, if they're going to give you, because these actually come from the course exam and description, they are going to basically have to give you that electric permittivity for the material because they actually don't provide many charts on the formula sheet. So this would be something, and you don't know material they're going to use. I mean, they could go anywhere from paper to an oil to glass, right, to air versus vacuum to water. Okay, so they would have to provide that for you, and you can already kind of see the equation stuck over here to the right. And this is the equation right here. So kappa equals epsilon over epsilon naught. Okay, and so this epsilon is, right, the electric permittivity for that material, which if I do a little bit of algebra, I can calculate that by doing kappa epsilon naught. Okay, and what you're going to see oftentimes is that the difference between dielectrics and capacitors is that kappa number. But the difference is, where do you put it? Is it in the numerator or is it in the denominator? Okay. So if you wanted to find, let's say, neoprene rubber, right? So E would be 9 times 10 to the 9th times 6.7. Right, so whatever that ends up being, that is the electric permittivity for that particular material. And then you can also substitute this relationship, right? Changes Gauss's law just a little bit, and we're going to do that in the example. So remember Gauss's law, integral of E dot dA equals Q over epsilon. Now, the reason why that you see with epsilon naught is because we're only talking about in a vacuum. But what happens if you have it in a capacitor, right? Well, that's where you end up with epsilon in the denominator, not epsilon naught. But this right here gets stuck right there, okay? And so for a dielectric, it would be Q over kappa epsilon naught, right? And then that would equal E times A. I basically just solved the first question for you, or the first part of the question of the example, okay? So we're going to kind of work with that right there to figure out the electric field in a capacitor, or a dielectric actually. Now, the electric field is created by a polarized dielectric, right? It's going to be opposite to the direction of the external field. The electric field between the plates, right, it's going to be essentially another way to calculate kappa, right? It's going to decrease when the dielectric is placed between the plates. Okay, so kappa is going to be, not epsilon, sorry. the original electric field divided by E, the new electric field. All right, and if you need to figure out kappa, or sorry, the new electric field, you're just going to do E0 over kappa. So remember, this here is no dielectric material. Okay. Oh, sorry, I was just grabbing the highlighter. This is with the dielectric material. So if they're looking at it without the material, they're going to call it E0 if they're calling it, or like with a subscript 0. And if they're looking for it with, it's just going to be no subscript. Okay, it's like final and initial. All right, now what happens also, the second you insert the dielectric material, you're going to change the capacitance. Okay, and so you can almost see this right here. It looks like it just says C, but it actually says C prime. So our new capacitance, which in this case, in that picture is C prime, is kappa times C original. Okay, but if you remember, C original was at epsilon naught A over D, but we mentioned this back in topic 10.3. The only difference was in topic 10.3, our kappa, because it was a vacuum permittivity scenario, was 1 because it was air, okay? And so that's why in the capacitor video is epsilon naught A over D, because capacitors are dielectrics with air between them. Excuse me. All right, you will get special cases too. You'll get the two lower ones here. So what these are series and parallel capacitors. They're actually, I think they're called compound capacitors, where it has an effective capacitance essentially, okay, that you have to find. So in the first one, these are called parallel. And so what happens is the E field will go pass through each of them, right? And in this picture, it's basically going to cut the area in half, but AP may change it and say, okay, 3/4 and 1/4, 1/3 and 2/3, or, you know, little gap, right? They're like a little gap question with air. So the effective, so this is the parallel side, right? That's our parallel side. So the effective capacitance is going to be C equals 1/2 kappa 1 plus kappa 2 times the original. Okay, but that 1/2 number comes from, because in our picture there, it splits it in half. So you have to go back and kind of do a little bit of algebra to figure this out. But good news is I'm going to create another video showing you how do you calculate the effective capacitance of these compound dielectrics. And now remember, it doesn't have to both be like, let's say, nylon and paper. It could be nylon and air, right? It doesn't have to be two like significant dielectric materials, if you want to say that. The other one could be air or vacuum. Okay, this is why I say that the tiny little question, which actually comes into the next one, which this is what we call a series. Okay, because essentially in the top one, the electric field has a kind of a choice to go through, right? So it can choose which way it wants to go. But in the bottom one, it has to pass through both of those dielectric materials. So the electric field will pass down, right, through both of them, where the distance for each dielectric material is 1/2. Again, AP likes to play around with that half number. It could be 1/3, 2/3, it could be 1/4, 3/4. But they may also do like, hey, a total distance of 9 millimeters, but 3 nanometers of that is air, right? It could be paper on top of like a very small sliver of air, like that big, right? Like that big. Okay, so you just have to read the question. And again, I will show you how this plays out. The equation that you see here, again, is the scenario with D over 2. So you end up with C equals 2 kappa 1 kappa 2 over K1 plus, or kappa 1 plus kappa 2. Okay, so right now, these are not equations given to you, so you need to memorize them. Don't forget the memorization process. And so you'd have to memorize these for the test, unless they're asking you to derive it. You'd have to show the steps to do it. But we'll also get practice when we do this in Unit 11, when we talk about what are called resistor capacitor circuits, which are RC circuits, and they may have like a dielectric running around in there like this. Okay, but also some of the calculations we have to do the calculation you have to do for this particular example, or with the plates with the multiple dielectrics in it, that's another thing. They can put like 4 dielectrics in there if they want, which changes like how many times you have to go, right? How many capacitors you have or kappas you have running around in there. It actually comes from the equation for that. For how do we work with these in series and circuits, or series and parallel circuits. All right, so let's do an example. So here you have a capacitor consisting of 2 conducting coaxial cylindrical shells of radius A and B, respectively. And so these are shells, right? And they tell you that L is much greater. That's a double greater than sign, means much, much greater than. So the reason why they say much, much greater is you don't have the effects of the edges. Then it's filled with oil that has a dielectric constant of kappa. So initially both cylinders are uncharged, but then a battery is used to charge the capacitor. That is the purpose of capacitors, okay? If you live in a hot region, aka Texas, you do not want the air conditioner blowing. The first thing, or stop working, the first thing that technicians will check is a component called a capacitor. And so that is the first thing they will check. They'll run a voltmeter through it and say, hey, there's nothing going to this, which means that's not working. So it's out of the circuit of the air conditioner. Run to the truck, because they usually have them on hand. Stick it in, you have air again. Okay. So what we're going to do is we're going to charge the capacitor. You're going to have a plus Q charge on the inner cylinder and a negative Q charge on the outer cylinder, as shown. And let R be the radial distance from the axis of the capacitor. Okay. And so we're going to determine 3 things: the electric field from A to B, the electric potential from A to B, and then we're going to do the capacitance of the capacitor. Now, A to B, even though it's shaded, sometimes in questions that signifies that it's a conducting material. That's actually the oil. Okay, the shells, the thin shells there are the actual conducting material. Okay. All right, and I'll give you an easy question to start, right? What is the electric field greater than B? Well, trick question is 0, because you have a negative and a positive charge essentially canceling each other out, so you have no net charge on the inside. So if R is greater than B, the electric field is 0, okay? Which just means now that surface is an equipotential surface, right? Go back to our rules for conductors, okay? But that's not what we're here to calculate, okay? What we're here to calculate, part A. I'm going to have to write small, because there's going to be a fair. So students always ask, please provide us examples of calculus. Here's that question, right? So there's going to be 2 parts of calculus and then a simple plugging in to figure out the last part. All right. So as we mentioned when we were just doing the notes, right? The first part is an application of Gauss's law, right? So we're going to do integral E dot dA equals Q over epsilon. But now, because this is the oil, right, we're looking for basically the electric field in the oil. It's not epsilon naught. This is no longer permittivity, vacuum permittivity. This is the material permittivity. But remember, we said for that, we're just going to substitute in kappa over epsilon naught. Okay, so now we do the integral. Again, remember Gauss's law at this level is just simply it's always just going to be EA equals Q over kappa epsilon naught, right? So I took that equation we just wrote, substituted in here. The integral is always just going to be EA, but the surface area is this as a cylinder, right? It's the length of the cylinder, so that is going to be 2 pi RL, okay? Actually, I'm going to write a lowercase r, because technically in the next section, that's what we're going to integrate through, okay? So Q over kappa epsilon naught. And so we divide both sides by this 2 pi RL, which comes down here with that mess. All right, and so the electric field from A to B is the amount of charge, right, over 2 pi R. It's always, where do you plug this stuff in, right? How do you make this look nice? So let's do this. Here's how we're going to write this. We're going to write this with our constants out front, and then the one that we're going to integrate or derive through last, okay? So here is, oh, that's dark, sorry. I don't know if I can erase just that. No, I have to rewrite it. Okay. So I'll just box it. So E equals Q, right, over kappa epsilon naught, so 2 there. Try to put the numbers up front, right? So those are our constants in the denominator, okay? And so there is our electric field inside the oil, basically, right? So it's Q over 2 kappa epsilon naught pi L R, right? So that's the first part. That's part A. Now we're going to do part B, which is what is the potential difference, right? The electric potential from A to B. So V is equal to negative E dot dr. So see why I kept the R to the outside, right? So we're going to do V, and we're going to go from A to B, right? And we'll do a little trick here to show you that it's easier to actually do it from B to A. This way we can get rid of the negative sign. It's a lot easier to work with. And so we're going to do the integral from B to A, right? That eliminates the negative sign. Our electric field, Q over 2 kappa epsilon naught pi L, constant, times 1 over R dr. Okay, I'm trying to leave space for part C. Okay, that's what I'm trying to do here. So I'm not going to cross this boundary. Okay, so we pull out our constants. Again, if you're not comfortable with the calculus set of integrals, rewrite as much as you can. Right, the integral from B to A of 1 over R dr. Now, 1 over R dr, if you did R to the negative 1, took the integral of that, you end up with like 1 over 0 R to the 0. Problem is that 1 over 0, R to the 0 is fine. That's, 1. Problem is that the fraction out front, the 1 over 0. So the integral of 1 over R, 1 over X dr is natural log of R. Okay. So we're going to do Q over 2 pi. See, I keep messing up where to write things. Okay. So 2 kappa epsilon naught pi L. We know what our answer is. We know it's going to be ln of R. And we're evaluating that from A to B. So ln of R evaluated from B to A is going to be ln B minus ln A. Oh, algebra 2, you learned log properties. If you're subtracting them, that just becomes division. Right? So ln of B over A. So I'm going to substitute that all over here. So Q over 2 kappa epsilon naught pi L times ln of B over A. So right there is our potential. Okay, in that area, in that region of the oil. All right, now we're going to finally do our capacitance. So capacitance is Q over V. That's very easy because Q is a constant and our V is our answer to part B. Okay, so we're going to just substitute that in, and it's going to look messy for a little bit. So we got 2, I put pi, 2 pi. I would like 2 pi's. Pi's are fun. So 2 kappa epsilon naught pi L times natural log of B over A. Okay. These Q's cancel because like this is the numerator Q. This is the Q that came from the V. And so what happens, basically, because now this is 1 over, so that whole mess goes up top, leaving just the natural log of B over A in the, so we got 2 kappa epsilon naught pi L divided by a natural log of B divided by A. So there is our capacitance. I know it's crazy, right? But there is how you find the electric field using a dielectric material. Okay, so that's the end of Unit 10. This has been remember the first 2 videos a little bit of review, kind of focusing on that electrostatics and conductors. These last two videos are going to help set up some information moving forward into Unit 11. But this is the Unit 10 conductors, capacitors, and dielectrics. That's the old title. They took out the dielectric portion, so now it's just conductors and capacitors unit.